Hello, my name is Ron Dorn. I'm a professor of Geographical Sciences and Urban Planning, and it's my pleasure to present to you a presentation about Earth spheres and their interactions for the Global Change GPH314 course. The purpose of this presentation is to give you an understanding of just how unique Earth is in our solar system by analyzing the different interactions of the different spheres associated with our planet. This presentation will have 4 parts: Earth as a system, the major Earth subsystems or spheres, why these are unique in the solar system, and some key interactions among and between the spheres. Earth, as seen from the moon, is an intact, holistic, fairly closed system, but there are different subsystems: the atmosphere, the realm of air, the hydrosphere, water, geosphere, sometimes called the lithosphere, the realm of the solid Earth, and the biosphere, realm of life. Solar energy drives the energy for the system, although there is some coming from the planet itself. One aspect why Earth is unique in the solar system, dealing with the hydrosphere, is we have abundant liquid water. Liquid water allows chemical reactions in your body, amongst the biosphere, between the spheres. It's the liquid water that really sets Earth apart. There may be liquid water on Mars, but that's up for debate whether it's truly in a liquid phase and how often it is, and how the liquid and the solid and the vapor phase interacts. Another reason why Earth is unique in the solar system is that the mass of the planet holds just the right atmospheric composition. An example of a planet with too much mass would be Jupiter or Saturn, in which you're holding hydrogen, and that gives you methane and ammonia. Mars would be an example of a planet with too little mass because it has very little atmosphere. We're just right. So Mars is too thin, Earth is just right, and Venus would be an example of an atmosphere where it's just too thick. Another aspect for our planet system is that we have an atmosphere that stops fairly lethal ultraviolet radiation. In the second layer of the atmosphere, or the stratosphere, there's an ozone layer, and that helps protect life on the planet's surface. Earth is also unique because the atmosphere is just right, keeping the temperature even. So if you were to go to the moon during the daytime, the temperature would be 250 F. At night, minus 250. So you have this massive diurnal swing in temperature. And Venus has a runaway greenhouse effect in which it's always hot. In contrast, even though it sometimes gets too warm or sometimes too cold, planet Earth has a fairly even temperature with minor diurnal or daily swings. One aspect of the Earth's hydrosphere that is fairly unique is that we have water in all 3 phases: solid, gas, and liquid. And there's energy exchange when the water changes phase. So these phase changes are a really important part of the planet's habitability. So you can think of the phase changes of water being a ladder of energy. Down at the bottom of the ladder is ice, then liquid water, and then water vapor. And it takes a lot of energy to move up the ladder, and this energy is released when you move down the ladder. So think about the planet's tropics. A lot of the water is evaporated into water vapor in the tropics. Then the tropical water vapor will move north with hurricanes and other storm systems, and then the energy will be released. It's all part of the magic of how the Earth works and equilibrates itself. We have an electrical field. Venus's electrical field is too intense. Our electrical field is just right. So when water molecules rise up into the atmosphere, sunlight breaks apart the water into hydrogen and oxygen, which then are carried away by the electrical field. It's pretty cool. But one of my favorite aspects of our planetary system is the magnetosphere. It's an interaction between the solid Earth and then the surrounding solar wind that invades the solar system. Our magnetosphere helps deflect the solar wind around the planet, protecting the atmosphere. And if we lost our magnetosphere, well, you might get Mars. Mars may have had life, and a long time ago, almost all of its atmosphere, when the core solidified, and the thinking is that the magnetosphere was lost at that time, and then the atmosphere was stripped mostly by the solar wind. Think about the spin of the Earth. It gives you night and day, but it also gives you what's called the Coriolis effect. The spinning of the Coriolis effect allows storm systems to work and operate, but if we had a planet that was spinning too fast like Jupiter, you'd have storms that would be utterly chaotic. So it's just the right amount of spin to give us the dynamics we need in the atmosphere. So if you move on to the biosphere, there's a question, are we alone in the universe? You have your opinion, other people have their opinion. It's up for scientific analysis. So now we move on to key interactions between the different spheres, and I would like to highlight one of these key interactions being carbon dioxide between the atmosphere and the solid Earth. There's a hypothesis called the faint sun hypothesis. So if you look at the graph, there's time over a 4 billion year period. And if you also look at the graph, there's the luminosity of the sun and the mean temperature of the sun. So what I want you to focus on is that the solar luminosity, the solar physicists tell us, have been steadily increasing over the planet's history, yet the temperature has remained fairly constant. There have been ice ages and hot periods, but basically for 4 billion years, we've been a fairly even temperature. How does that happen? How do you get solar radiation increasing and also maintaining temperature? The solution rests in the interaction between spheres and the reduction of carbon dioxide over time. The photograph you're seeing is a rock called limestone. Limestone is composed of calcium carbonate. So what's been happening, the thought is over the last 4 billion years, is that the minerals that contain calcium in silicates. So if you look at the equation, there's CO2 plus calcium silicates. Then there's the decay of the calcium silicates. The calcium released from the minerals, the silicate minerals, combines with the carbon dioxide in the form of CO3, and limestone is deposited. So the limestone that is a major sedimentary rock is really that stored carbon dioxide over a 4 billion year time frame. Some of my research has been involved in this. If you look at the temperature history of the Earth and focus on the far right or the Cenozoic, you'll notice that the average global temperature started to decline in the middle of the Tertiary period, in the Cenozoic. There may be a crazy idea. Ants. Ants started to develop about this time, and ants have the ability to dissolve the calcium silicates more than almost any other agent. So the ants enhance the decay of the calcium silicate that can combine with the CO2 and begin to drop our planetary temperature. It's an intriguing idea and an example of the interaction between the biosphere, the atmosphere, and the solid Earth. Another key interaction is the buildup of ozone over time. Nobody really knows exactly the history of the ozone layer, but there's a thought that it started somewhere around 1 billion years ago. And the key was that free oxygen that was being released with photosynthesis would move up into the stratosphere. Solar radiation would combine the oxygen, the O2, into making O3, and we'd gradually build up the ozone layer as life got more and more protection. You'd be able to build up the ozone layer until an equilibrium or a balance was reached between natural buildup and destruction. Of course, humans get involved and the ozone layer is in trouble. Another key interaction that may interest you is the development of placental mammals. I don't know about you, but I'm a placental mammal. I was in my mother's uterus, not in a kangaroo's pouch. And I think it was a pretty cool way to develop safely. You probably feel the same way. And there's a thought that the reason why placental mammals could be developing or could develop was because an increase in the amount of oxygen in the atmosphere at that time. So that would be an example of the interaction between the atmosphere and evolution. We were almost an ice ball planet. We were in serious trouble about 700 million years ago. The Earth's surface was covered in a lot more ice than even the last ice ages. And what happened? The oceans came to the rescue. Methane was released that increased the greenhouse effect, and the snowball Earth was stopped. In summary, Earth has a unique system of atmosphere, solid Earth, water, and the biosphere. And as far as we know, incredibly precious. as a college-educated person, I believe it's important for you to communicate this to your friends and your family. Thank you.